Hey everybody, welcome back. Mr. G here again. Today we're going to talk about transformers. So we're going to look at things like what is a transformer, what's its job, how does it work, and some of the basic concepts around a transformer. So for further information, we have our textbook, Principles of Electric Circuits, Conventional Current Flow, by Floyd and Buckla. Transformers are in chapter 14 in this book. So, chapter number 14, sections 1 through 4 is what we're covering in the Tech 150 class. So, chapter 14, 1 through 4. So, what is a transformer? Now, every time I ask that in class, I always get somebody saying, well, transformers are robots in disguise. Well, that's true, but not in our particular case. So what is a transformer? By definition, a transformer is a machine. It's a machine because it actually does a job. So a transformer is a machine whose job it is to convert one value of electrical energy into another value of electrical energy. So if you take electrical energy, the job of a transformer is to convert that energy into another level of electrical energy. So a job of a transformer is to convert one value of electrical energy into another value of electrical energy. Now, if you have taken science previously, you should know that there is a law of energy conversion, and basically what that law says, that energy cannot be created nor destroyed, but only changed in form. So in our case, the transformer is changing the electrical properties from one form to another form. Still remaining electrical. This energy is somehow converted into this energy. And what we're going to do is we're going to take a look and see how this actually works. So, a transformer is made up of a core. And now there are many types of transformers. We're going to stick with the most basic power transformer. It's made up of a core material. Typically that core material is made up of iron. Iron is very, very permeable, which means that it has the ability to set up magnetic fields. Okay, so it has the ability to set up a magnetic field. It can be magnetized very, very easily. So the core material is made up of iron, and we have two coils. So we have a coil wrapped around one side of the core, and we'll call this the primary. And then we have another coil wrapped around the other side, and we'll call this the secondary. So three main parts to a transformer. The first part is called the core. Then we have a primary winding, and we have a secondary winding. So basically what happens is electricity is fed into the primary side. So what kind of electricity? It is AC. Transformers are AC devices. So an AC waveform is put into the primary side of a transformer. What we get on the secondary side is AC coming out of the transformer. Now, again, it's electrical energy, electrical energy. What's the difference? Well, the difference will be in the values of voltages and currents as they appear on primary compared to secondary side. So how does a transformer work? A transformer works on the concept known as mutual inductance. Now, what mutual inductance means is that a magnetic field is created, and that same magnetic field is being shared. So therefore, a magnetic field is common to the primary and to the secondary windings. So when two coils are affected by the same magnetic field, that's what's called mutual inductance. So how does the magnetic field actually work? Well, one of the properties of an electrical conductor is when you put current through the conductor, a magnetic field is actually generated around that conductor. So, basically what that says is, if we have a coil on the primary side and we put electricity into that coil, what is actually created in that coil is a magnetic field. That magnetic field is known as flux. It has the Greek symbol phi, and that is the flux. The job of the core is to direct the flux from the primary side, which is creating it, into the secondary side. So basically, the flux flows through the core. So again, the job of the core of the transformer is to be able to direct the flux, the flow of the magnetic field. So the magnetic field from this coil here is then directed through the core and down the center of this other coil. When a magnetic field interacts with a conductor, it actually creates electrical voltage and current. So when I apply voltage to a coil or a conductor, it creates a magnetic field. The opposite is also true if I take a magnetic field and induce it into a coil. We get an induced voltage. So, on the primary side, we apply an AC waveform. It creates a magnetic field. In turn, that magnetic field creates a voltage on the secondary coil. So that's all based on mutual inductance. They share that same magnetic field. And the core's job is to direct that magnetic field from the primary into the secondary. So, what else does the transformer do for us? Well, one very important thing that a transformer gives us is known as electrical isolation. Electrical isolation, what does that mean? It means that there is no electrical connection between the secondary and the primary of a transformer. There's no wire that joins the primary side and secondary. There's no way that electricity from this side gets directly to that side. The only way it happens is through a magnetic field. So the only thing that links the primary to the secondary is actually the magnetic field, otherwise known as the flux. So these two are electrically isolated from each other. The only thing that joins them is a magnetic field. No electrical properties or no electrical connection at all between the two. Just a magnetic field. So, how does this all help us? Well, what we need to do is we need to apply some signal over on the primary side, and it's somehow going to create something onto the secondary side. The levels, so voltage here compared to voltage here, could change. So we could have something called a step up transformer. A step up transformer means that the primary voltage gets boosted before it gets to the secondary. So it comes out on the secondary larger. So on the primary side, it is small. On the secondary side, it comes out larger. And that is with respect to voltage. On a step down transformer, on the primary side, we have a large voltage, and the value as it appears on the secondary is actually smaller. So step up, the primary is small, secondary is larger. So that means the value of voltage increases. Step down means that the value on the primary side is larger and the value on the secondary, resulting secondary, is smaller. There's also something known as an isolation transformer. An isolation transformer is a specific transformer where the voltage on the primary is actually equal to the voltage on the secondary. So in an isolation transformer, these two values are the same. But what it allows us to do is implement this electrical isolation between the two circuits. So we have a primary circuit, secondary circuit. So anytime we want to isolate two circuits in an AC world without changing the voltages, we can actually put in what's known as an isolation transformer. So now let's take a look at things like step up and step down transformers and how does that all work. So again, I'm going to just take a schematic symbol. This is typically a schematic symbol for a step down transformer. Step-down transformer has more windings on the primary side than on the secondary side. Now, how does that actually translate into voltage being smaller on the secondary? So here's what I'm going to do. I'm going to go back to this other diagram here for a second. And you can see that the flux, or the magnetic field, is what joins this primary to this secondary winding. So it's the flux that actually does that. What creates the flux? Well, the flux is actually created by this value of voltage being applied to this winding. So if I take that same concept and I say that the flux is actually created by taking a voltage and applying it to a winding. So a winding has a certain number of turns. So flux is created by a certain voltage and a certain number of turns. So flux is created by a certain voltage being present over a certain number of turns. Now that flux flows through this other coil. So that flux that was created at a certain strength, so it was created, the strength of that flux is based on voltage and turns, what created it. So now that flux flows through the core to get to the secondary. So that flux that was created by a certain amount of voltage over a certain amount of turns now flows through and gets to the secondary. So now, how much voltage is created here is based on that strength of the flux and the number of turns. So the flux and the number of turns. That's what ends up creating the voltage on the secondary. So the strength of the flux flowing through and a certain number of turns. So if I give an example, on the primary side, let's say I had, let's say 120 volts. 120 volts of AC coming in on the primary side. On the primary side, let's pretend I had 60 turns. So on the primary side, 60 turns. On the secondary side, let's say I had 30 turns. So, if I go back to the other picture, this flux was created based upon, see if I can get both those in the camera for you, there we go. So this flux was based upon voltage and turns that created it. The voltage was 120 volts, the turns were 60. So if I said 120 volts over 60 turns, so that means that the strength of this magnetic field was created at 2 volts per turn. So 2 volts per turn is what created that magnetic field. So now that magnetic field flows through the core and finally gets to the secondary. So it flows through the core, gets to the secondary. The strength of that flux was based on 2 volts per turn. So What do you think's going to happen when that magnetic field or that flux flows through this winding at the same strength? What will happen is it will induce a voltage on this coil based on this strength. So the flux is flowing through at 2 volts per turn, and I have 30 turns. So therefore, the voltage that creates on the secondary is 2 volts times 30 turns. So it's 2 volt per turn times 30 turns is 60 volts. So what's coming out on the secondary is induced over here, and it is 60 volts. So in this example, 120 volts of AC is going into the transformer through 60 turns. Creates a magnetic field based on this strength. That strength flowing through the other winding creates a voltage that is based on that strength. So we have the strength of the magnetic field, which is 2 volts per turn. 30 turns gives us 60 volts. So this is a step down transformer. So the value of voltage steps down. So that means there are more turns on the primary side than there are on the secondary side. If we take the same thing, but now we create it the other way. On the primary side and on the secondary side. So on the primary side, again, I put in my 120 volts and I have my same 60 turns. The magnetic field strength, again, is 120. So the magnetic strength is still 2 volts per turn. That magnetic field is passed on to the secondary. Let's say the secondary has 120 volts, or 120 turns. So now, when I look at the voltage that comes out on the secondary side, it's 2 volts per turn times 120 turns, giving us 240 volts. So therefore, this is a step up. So the secondary is larger than the primary, a step up transformer. So if that is a step down, and this is a step up, when we look at the isolation, the number of turns is exactly the same. So if I had 120 turns, I get 120 turns. So if I place 120 volts, I get 120 volts. If I put in 60 volts, I get out 60 volts. That is an isolation transformer. The advantage, you are getting the electrical isolation between the two. So, what is the relationship between the voltage on the primary side and the voltage on the secondary side and the number of turns? Well, that relationship is described as the turns ratio. The turns ratio is denoted by the letter N. And basically the turns ratio says that the turns, so the number of turns on the secondary divided by the number of turns on the primary give you the turns ratio. So again, that is denoted by the letter N. That also translates into the voltage on the secondary divided by the voltage on the primary. So that is turns ratio. So how does that actually work? So let's say I have a transformer. If I have on that transformer 60 turns on the primary side, 30 turns on the secondary side, that gives me a turns ratio equal to the secondary, which is 30, divided by the primary, which is 60, which is equal to 0.5. So turns ratio of 0.5. That's what my turns ratio happens to be in this example. So how does that translate into voltage? Well, if I look back at this formula here, I can see that N is equal to the voltage on the secondary divided by voltage on the primary. So if I took a voltage on the primary over on this side and applied it, and let's say that voltage was 120 volts. So now this works out to be, my turns ratio is 0.5 is equal to voltage on the secondary divided by 120 volts on the primary. When I work that all out, it comes out to be the voltage on the secondary is equal to 60 volts. So if I apply 120 volts into a 60 turn transformer primary with a 30 turn secondary, I will get 60 volts coming out of that transformer. That is a turns ratio analysis. As you move further into your studies, you might come across something that is referred to as the transformation ratio. The transformation ratio is denoted by the letter A and is the turns on the primary divided by turns on the secondary equals the voltage on the primary and the voltage on the secondary. So the two are actually opposites. Whereas this will give us a turns ratio of 0.05. Same circuit over here will actually give us a transformation ratio of 2. Turns ratio is secondary over primary denoted by N. Transformation ratio is primary over secondary denoted by A. Now, for what we're talking about, we're going to look at the turns ratio. That is what our book is using. But I just wanted to bring that up, transformation ratio, so you've seen it. If you do further studies in electronics and electrical, you're going to come across the transformation ratio. And I just wanted you to know how it is different. So turns ratio is what our book uses right now. It is going to be the letter N that is denoted, and it is the secondary over the primary. So secondary turns over primary turns equates to secondary voltage over primary voltage. So that's the relationship between the turns and the voltages that are present. So this is an example for a step-down transformer. So applying larger voltage, we get smaller voltage coming out. Hope that makes sense so far. All right. So, in a transformer, I had said that energy cannot be created nor destroyed, but only changed in form. So if I apply 120 volts on the primary side of a step-down transformer, and let's say I get 60 volts coming out of that transformer, since I cannot create or destroy energy, only change its form, seems to be losing some energy here. But the law says that I can't. So something else must be going on, because we can't break the law. So something else must be going on inside this transformer. So where that happens, if we looked at this, this is voltage and voltage. So these are two voltages. As we know, in electricity, there's more than just voltage happening. There's also current and power. So power is the total, if you will. So power is energy over time. So since energy cannot be created nor destroyed, but only changed in form, power must abide by those same rules. So power cannot be created nor destroyed. So if I have power input and I can't create or destroy, when I look at the power output, they must be the same. And in an ideal transformer, they are. So power in a transformer is equal to the power out. Oops, yeah, power, that's right. Power out of the transformer. So power in is equal to power out. But the voltages have changed. If power is not created nor destroyed and must remain the same in both, so power in equals power out, the voltage has changed. But we know from our basic electronics that power is made up of not only voltage, but current. So, if the voltage drops, what do you think must happen to the current in order to keep the power in equal to the power out? So, if the voltage goes down, the current must go up in order to keep the power equal on both sides. So, just as an example, if I had on the primary side, if I had voltage, so voltage on the primary side times current on the primary side, that must equal voltage on the secondary times current on the secondary. Those must be equal because power in must equal power out. So in a step-down transformer, when the voltage goes down, the current goes up. On a step-up transformer, when the voltage goes up, the current must fall. This statement must remain true. So what we're going to do is we're going to look at an example where we're going to perform some of these calculations. So let's take an example. So the example is going to go something like this. I'm going to have a step-down transformer, and I'm going to have 120 volts being applied to that transformer. I'm going to say that this is our 60-turn transformer, and I'm going to say over here is my 30-turn secondary, and I have this going to a resistor, and let's say the resistor is 1 kilo ohm. So I'm going to solve for all this stuff. So I'm going to solve for this circuit. So here is my transformer, 60 turns, 30 turns. I now have a load, if you will, on the secondary side. We'll call it 1K. So we have voltage applied. That's known. Primary turns, that's known. Secondary turns, that's known. What is not known is how much current flows on the primary side, how much voltage appears on the secondary side, how much current appears on the secondary side. So we know the primary voltage, we know the number of turns, the rest we need to calculate. So, first thing we're going to look at, we've got what's our turns ratio. So our turns ratio is the secondary number of turns, so N on the secondary over N on the primary. So that equals 30 over 60. So that equals 0.5. So our turns ratio, N, is 0.5. So now we can use the turns ratio to calculate the secondary voltage. So just like before, the voltage on the secondary is equal to the turns ratio times the voltage on the primary. So in this case, it's 0.5 times 120 volts, giving us 60 volts. So now we take that 60 volts and we're going to put it up into here. So that's 60 volts. So in this transformer circuit, we got 60 volts across that resistor. So 30 volts, that 30 turns gives us 60 volts. So we got 60 volts and we have 1K. So if we want to find the secondary current, so secondary current, Ohm's law tells us that it is the voltage on the secondary divided by the 1K. So that's 1 kilo ohm. So that works out to be 60 volts divided by 1 kiloohm gives us 60 milliamps of current. So the secondary current here is 60 milliamps. So now what is left is this primary current. How much current is flowing on the primary side? Well, we know that power in must equal power out. So therefore we know that 60 volts times 60 milliamps must equal 120 volts times I primary. So power in must equal power out. So 60 volts, so power out is voltage times current on the secondary side. Power in is voltage times current on the primary side. They are equal. So you can rearrange these numbers, if you will, and therefore solve for IP. Now, I did say that on a step-down transformer, when the voltage goes down, the current must go up. So that means that this current must be larger than this current. Okay, so again, this current must be larger than this current. So if we actually did this math, we would see that IP is equal to, and we've got 60 volts times 60 milliamps divided by 120 volts. So the 60 volts, that works out, and what we end up with is IP is equal to 60 milliamps divided by 2 equals 30 milliamps on the primary side. So if I take 120 volts multiplied by 30 milliamps, so I take my calculator and I do 120 volts times 30 milliamps equals 3.6 watts. If I take 60 volts times 60 milliamps, I get 3.6 watts. So, as the voltage goes down on the secondary, the current must go up. Okay, so as the voltage goes down, the current must go up. If the voltage was to go up, the current must go down. Again, if the voltage was to go up, the current must go down. So that's the basic math behind the principle. So I'm just going to put that right there and show you one last bit here. If N, so that's the turns ratio, is equal to secondary over N primary, which is also equal to the voltage on the secondary over the voltage on the primary. And as we saw in this example, in a step-down transformer, If the voltage goes down, the current must go up. So this relationship actually translates to current in the primary over current in the secondary. So turns ratio is a relationship between the turns of the secondary over the primary, which translates to voltage over secondary, or voltage of secondary over voltage of primary, which I also claim is equal to the current of the primary divided by the current of the secondary. So if I go back to this example, and I'm just going to bring that and put it right here and keep everything right there. We figured out N, okay, so N itself is 0.5. So that's what we figured out, 0.5. How did we figure it out? Well, what we did is we did 30 divided by 60. So this is the turns. So when we look at turns, 30 over 60, 0.5. Voltage. So we've got voltage, 120, and we've got 60. So if we looked at the voltage, 60 volts on the secondary, 60 volts on the secondary, 120 volts on the primary equals 0.5. Now we have current. So current on the primary is 30 milliamps. Current on the secondary is 60 milliamps. Again, 0.5. So the turns ratio has a relationship between the number of turns, the voltages, and the currents as well. Okay, so again, the turns ratio, N, has a relationship between the number of turns, the voltages, as well as the currents. Well, I hope this helps. For more information, you can refer to, again, the textbook. So our textbook is Principles of Electric Circuits. The information that we're getting is from chapter number 14. You'll find this stuff in 14-1, 14-2, 14-3, and 14-4. So those 4 sections of chapter 14. Well, I hope this works and makes sense to everybody. So please take care. Until we meet again next time, have a great day.